Hi there, this is Andy for another video on electronics development. This video is the first in a series which I'm calling Electronics Toolkits. The Electronics Toolkits videos are, I hope, designed to give you some techniques and ideas to get you out of a hole when designing kit. This first one will be on how to convert bipolar signals to unipolar signals. This can sometimes be handy if you have a microcontroller which generally have unipolar inputs, or a discrete unipolar ADC, and someone then drops you a requirement on you, as they sometimes do, to be able to interface to a sensor or a function that has a bipolar analog output. Okay, so let's see how we do this. So on the screen is a block diagram of what I'm proposing. In actual fact, that's what we use generally in the industry to do this task. Going from left to right, you'll see that we have a function which is called bipolar to uni conversion network. And in this example, it's going to take plus or minus 10 volts in. The output I hope to show you will be from 0 volts to the voltage reference. It then gets applied to a rail-to-rail input-output buffer, so we don't have any common mode issues. That buffer is used then to drive a post-buffer low-pass filter, which is a simple RC function, and then it's interfaced to the unipolar ADC input. Now, the reason why we obviously have a low pass filter is for anti-aliasing, but the other reason is generally capacitive ADCs like to be driven with a low source impedance, and while you're at it you may as well make a low pass filter out of it, because a lot of the time you want that capacitor, which in this instance is CLPF. You place that next to the input of your ADC and you get a very tight current loop, so you're not dragging that pulse of current when it switches. So what happens in a capacitive ADC, it'll switch, it'll grab a pulse of current, and sometimes you'll get, if you have such a high impedance, you'll get a bit of a droop voltage. So we have a capacitor there that supplies that instantaneous charge, and that helps us maintain accuracy. So what I'm going to show you is the network first, and how it converts plus or minus 10 volts to the VREF, 0 to VREF. So the program I've got here is Symmetrics. This is the free version. Symmetrics is a very, very good spice simulator. It's what we use in the industry. There's many good spice simulators. Microcap is another great one. There's LT Spice, obviously. There's quite a few, but for this example we're going to use Symmetric. So what I'm going to do is draw the network. So I'm just going to drop a couple of resistors down here. Then we're going to rotate this one and put it there. Just don't show that. Just draw it up. So what we're going to do now is put a voltage reference. Now the voltage reference obviously feeds this network, but it would also power the rail-to-rail input output amplifier, and it would also power either the reference input, the ref high input to your microcontroller, or in the purpose of a discrete ADC, would power the discrete ADC, because these ADCs, they don't take much current. So I'm just going to change the values of the of these, and I'll tell you why a bit. Okay, so the next, what we're going to do is we're going to place another voltage source, but this one we're going to configure to be a sine wave generator. So what we want to try and convert, our boss has given us a function that we want to convert plus or minus 10 volts signals. So we have, it doesn't matter what frequency it is really, so for this instance. So we've got a sine wave, it's gonna rotate plus or minus 10 volt peak. It's running at 1 kilohertz, it's got no offset. So that's what that is. Okay, we're going to place a module port, and we'll call that bit. It's going to call it V out. I'm going to draw that there. We'll go to simulator. We'll choose our analysis. I'm sorry I'm going through quick. This isn't a tutorial on how to do symmetrics. I assume people can look that up or. So what I've done is I've set the print step to 1 mic because I want quite a fine granularity. I've set it to 2 milliseconds. It's a 1K signal, so I'm going to get two periods, and we'll hit run. Okay, so it's finished. I'm going to probe on the input, and you'll see that we have a lovely plus or minus 10 volts signal, as you'd expect, because that's what we programmed it to do. On the output, well, there you go. We have a 0 to 5 volts signal, and it's centered at 2.5, which is what we really want. So just to get some figures on it, so we'll measure the peak to peak, and we'll say we want to look at V2, which is this one here, and that will tell us down here that it's 20 volts. Of course, plus or minus 10 volts added together is 20 volts. Okay, so we'll do it again. More functions, peak to peak, and we'll look at Vouts, and there we go, 5 volts. So that's confirmed that. So in this simple network, we've converted a plus or minus 10 volt signal into a 5 volt signal. Very simply, I might add. The other thing as well is we've got a 1.5k resistor here. Now, if you bought an array of 3k resistors, so an array which has 4 3k resistors in, then typically they are pretty well matched. So what you can do is you can go, well, I'm going to say this is 3k. I'm going to add another one on, obviously, because I want it to be 1.5. There we go. And we'll run it again. Let's just get rid of these. Probe to make sure we are doing what we're supposed to be doing. And there you go. So it's gone from 0 to 5 volts. They'll be well matched, well toleranced. They should be well matched from a drift and aging point of view. So it's a very cheap way of converting a plus or minus 10 volt signal into a 5 volt signal. Okay. Now, while I'm at it, one of the things, a bit of a pro tip on this. It may seem common sense whilst I'm saying it, but you'll be surprised how many people fall foul to this. But with regards to the voltage divider and the attenuation network that you're seeing on the screen now, and it can be any voltage divider. It could be an enable or one on a comparator. It could be a voltage setting for a power supply. So what you want to do is you want to make sure, if you want good tolerancing of that function, right, is to place all the parts on the same side of the card next to each other. It's quite key, this is, right? So put them all on top layer or all on bottom layer, but make sure they're all together in the same area as close as possible. Okay. Also, if you're going to do any rework task, So you get a unit back from the field that's been in service for 5-10 years, and for some reason you have to replace part of the network. Then it's generally best practice to replace all the parts of that network, and the reason is, when you replace all the parts of the network, you would replace them with parts that had the same sort of build time. They were produced at the same time, so all the aging effects that you would get by leaving half the parts on and then putting new parts on, well, you'd have tolerance issues because of aging of the old parts versus the new. So replace all the parts in the network, and then that keeps your tolerance calculations current. The other thing as well, like I said, putting them on the same side of the card, you get a lot of freedom going through your tolerance calculations, such as thermal drift, life, etc. Because thermally, they'll all be seeing the same temperature, so they'll all drift at the same point at the same time. So that's just a bit of a sort of a pro tip, really. A lot of people sort of dismiss this and they just place things all over the place, but try and keep them together local on the same side of the board, and you can get a much better tolerance out of some not so high price parts like an array of network, for instance. So this was just a short video really based on how to convert a bipolar signal to unipolar. There are many different ratios of resistors. I obviously haven't gone into how I've picked these ratios. I could do that if anybody's interested. Just send me a comment. But you can do these for 2.5 volt ADCs, 3.3 volt ADCs, 5 volt ADCs. It's just a way of manipulating the network. But to get good ratiometric cancellation, it is pretty key that you power the network off the same supply that you power the buffer amp, in this instance here, the buffer amp and the ADC. And like I say, if it's a discrete ADC, a standard reference will more than power this, and if it's an ADC like in a microcontroller, there normally is a cal high and cal low reference input for the ADC section. So you would pair that section, and then it's all ratiometric at that point. So I hope this was informative and it helps you in some way, and I hope to be doing more of these type of videos, these quick videos. Like I said, if you want any more information on the tolerancing or how the ratios work, then drop me a comment and I'll try and do a video on that. Okay. All right. Cheers. Okay.